Hello students, in the last lecture I had completed the theory behind torsion. Now to demonstrate the usage of formulas and how we will solve real problems, let us take the example of an elliptical cross section. Now remember that more simpler cross section than ellipse is to just take a circular cross section. But for circular cross section we already discussed that the solution of torsion is very simple because in the case of circular cross section there is no phenomenon of warping. So what complicates torsion or what requires the advanced solid mechanics uh, treatment of torsion, the problem of torsion of prismatic bars is the phenomenon of warping, which we had discussed in the earlier lecture, right? So if it is just simple circular bar, as I had shown you, you can go to an earlier section, section 87, in which they are discussing the formulas. So it is too simple. Okay, so let us discuss the solution of a torsion problem using the formulas we had discussed until last class of how to solve the problem of an ellipse. So ellipse, you know that it is similar to a circle, but you will have two radii, right? So you have a major axis, you have a minor axis. So here major axis, let it be a, and minor axis, let it be b. So the equation of ellipse is given by the following expression: x square by a square plus y square by b square equal to 1. So at the boundary you can substitute this will be, and so this is basically the expression for ellipse. So let us try to solve, or let us try to determine the stresses and displacements due to torsion in a elliptical bar. So we will use the formulas which we had derived last class. So remember what I said was, I have the lecture of last class open here. There are two approaches. One approach is you can use the two formulations we had arrived in the using warping function, or a more classical approach is to use the two formulas based on stress function. Okay, so the formulations using stress function is, especially in the boundary condition expression, tends to be more similar than that we had arrived for warping function. So let us solve this problem using stress function. So these are the two equations. So you have seen the nature of solution by stress function. So you have some conditions to be satisfied, which is these, and then we assume a form of stress function which satisfies these conditions, right? Now what it is seen is, see, in the case of torsion of prismatic bars, it's all about the shape of the bar, because the loading is only torsion, but remaining thing is about the shape of the bar. So usually it is seen that the solution takes the following form. So if this is the equation of ellipse, so you can take one to the other side and you can write it in this form. And what happens is, since you require the stress function to satisfy these equations, and especially the second equation which states that the stress function along the boundary d phi should be constant, right? Because d phi by ds equal to 0 means it is phi should be a constant along the boundary. S is the boundary. So we had discussed this in the last class. So to satisfy that, it is convenient to take the stress function in the following form. So where this is nothing but the equation of the ellipse, and m is a arbitrary constant. So what is m, that will determine. Okay, so if you take phi in this form, obviously needless to say it will identically satisfy this equation, because this is anyway 0, right? Now let us substitute it in the first equation to determine other other features of this particular stress function. So remember this again, I am repeating, these are our expressions based on stress function, where minus 2g theta we had also called it as f. Yeah, this is the formula. So that is what I have used here. So in order to substitute in this expression, you take the second derivatives of phi with respect to x and y. So that is what I have done here. So when you substitute that, you will get that f equates to this expression 2m into a square plus b square by a square by b square. So which means the m is a square b square by 2 into a square plus b square into f by taking this expression to other side. Now using this expression for m, we can substitute it back into this expression. We can get the final expression for stress function. But then what is f? That is the next question. Now for f we already have an expression, but let us try to relate it to the external torsional moment. So remember, the problem is driven by the external torsion, right? So if the external torsion is empty, like what we had assumed in the last lecture, then let us try to arrive an expression of f in terms of empty, because that will be more meaningful. So in the last lecture we had seen that empty is related to phi in the following form. So this was the last step of our last lecture. So here empty equal to double integral phi dx dy. So expression for phi we have, okay, this is the expression, where m also we had also already solved it in terms of f. So you substitute that and you simplify. So what you will get is this integral will split into three terms. So you have this first term, second term, third term. Now double integral x square dx dy. So in classical mechanics we know that it is nothing but second moment of area about y axis, right? X square dx dy. And for an ellipse you know that it is pi b a cube by 4. If it is a circle, obviously it simplifies to pi r raised to 4 by 4. So these are the expressions, right? So this is x square dx dy, second moment of inertia with respect to y, and double integral y square dx dy is second moment of inertia, or area, better to say area, second moment of area with respect to x. That expression also we know. And double integral dx dy is nothing but the area, okay? So actually what's happening is, see, this is how the definitions of Iy and Ix have come into the subject of solid mechanics. So this is just a side note, because in these expressions and similar derivations we are seeing terms like this, okay? So actually these terms are not used to validate Ix and Iy, rather Ix and Iy, terms similar to Ix and Iy are originating from these steps, because in the derivation from first principles we are seeing that there are terms like this, double integral x square dx dy and double integral y square dx dy, not just in torsional problem but in other problems as well. Anyway, so that is just a side note. So with these quantities you can substitute it into this expression. So the entire expression for empty simplifies to this particular expression. So empty is minus pi a cube b cube f by 2 into a square plus b square. Now remember, we were trying to relate f in terms of empty, right? So you can take all other terms other side. So f is written in terms of external torsion as this, okay? So we solved our problem to a certain extent. So this was our initial phi. Now m we arrived at expression in terms of f. So F we related in terms of external moment, external torsional moment. So this is the final expression for phi. Okay. So the expression for phi is ready. So with the expression for phi ready, we can calculate the stresses tau xz and tau yz. So remember, I am recapping. I will open the old lecture. For the torsion problem, we had already seen that these terms are zero. Only non-zero stresses are tau yz and tau zx. Tau yz and tau zx, in the last lecture we had written it in terms of stress function in the following form, right? Tau xz equal to dou phi by dou y and tau yz equal to minus dou phi by dou x. So now that we know the stress function, this is the expression for stress function, we can find out the stresses. So you will take first derivative. So these are the expressions for stresses tau xz and tau yz. So we can see that both are linear functions of coordinates. So tau xz is a linear function of y, and it makes sense because when you are trying to twist a bar, at the center there is no stress, and stress linearly increases as you increase along radial direction. Similarly, tau yz is a linear function of x. And what happens is, if you take the ratio of tau xz and tau yz, it will be a function which is ratio of y and x. So for those ratios of y by x which are constant, the ratio of tau xz by tau yz also will be constant. Okay. Now always we are interested in the maximum stress. So we got the expressions for stresses. So what will be the maximum stress? So one thing we know, as y and x increases, the stresses also increase. Okay. So out of tau xz and tau yz, which will be maximum? So the maximum will be the one which will have lower denominator. So remember, there is a b cube and a cube b, right? So first of all, maximum will be at the extreme end. So at y equal to b and x equal to a, you will have maximum. And further, here you have b cube in the expression for tau xz, which means tau xz will be lesser than tau yz. Okay, so maximum shear stress will be tau xz at y equal to b. So that expression we will see here. You substitute y equal to b, 1b will cancel. This is the maximum shear stress due to torsion. Okay, so the magnitude of this is 2mt by pi a b square. Now if it is a circle, we know that a equal to b, and the expression will simplify to following form: maximum for a circle. So this is the full problem for the full solution for the ellipse problem. But what we have arrived at so far is only in terms of stresses. So this is the maximum stress. Now let us solve the problem, or let us determine the twist. So we want to determine twist as well as we want to determine the special aspect, which is warping. So remember, we discussed that warping is what makes the problem of torsion complicated. Otherwise the solution of torsion even for non-circular bars will be much simpler. So it is the out of plane deformation, which is known as warping, when you have twist, that makes the problem of torsion complicated. So for warping, we had arrived at the following expression for W. This was our starting point, right? So let us determine for ellipse what will be the out of plane deformation that as a result of warping. So first let us solve for the twist. So remember, F equal to minus 2g theta, that we had added in the last lecture. Just show you that. Yeah, F equal to minus 2g theta. So you know what is F. You know g is known, modulus of rigidity. So using that you can calculate twist. Okay. Now So remember, this is twist per unit length, because that is what we had assumed here. Theta is twist per unit length. Now let us calculate the out of plane deformation, which is a manifestation of warping. So you have the body twisting like this. So what is the out of plane deformation or deformation along z direction, which is a result of warping? So the expression for W is theta phi xy. So theta already we determined. Now what is phi xy? Well, uh, actually, if you go to our previous lecture, we had written, see, tau x z, tau y z, it is related to warping function in the following form. Okay, this was also part of our earlier lecture. Yeah. So this is the expression for tau yz and tau zx, right? So tau yz and tau zx, we have already determined their formulas in this lecture itself. This is tau xz, this is tau yz. So in this particular expression, we know this, you know, expression for theta, which we just arrived at. Okay, so using this, either this first expression or second expression, either one of the expression, you can arrive at the expression for the warping function. So what you do is, you take any one expression and you integrate it. Okay, so here I have taken the expression for in terms of tau zx. So the expression will be something like this, because tau, the expression for tau zx you know, and expression for theta you know. So what we do is, see here, warping function is with respect to x. Okay, so you have to integrate this with respect to x. So integrate the entire expression with respect to x. So when you integrate y with respect to x, it's a constant. This is also independent of x, so it will be a constant. So you will have yx and this expression into x if you integrate both with respect to x. So you will get the expression for warping function. Then you have the term of theta, for which you can substitute what we have read here. So doing the necessary substitutions, the warping function will simplify to the following expression: mt b square minus a square into xy pi a cube by pi a cube b cube g. Now if it is a circle, a equal to b, okay, which means w equal to 0. So it agrees with what we have said. For a circular section, there is no warping. Okay, warping is 0. So it is perfectly fine, because when a equal to b, this expression is 0. So for all other values of a and b, this w will give you the out of plane deformation. So again, as I told you, it's important to get the physical feel. So remember, we are trying to solve this problem. So as what we said is, as a result of this torsion, there will be out of plane deformation along the z direction. So this w directly gives the out of plane deformation. Now let us try to plot this. Actually, I thought of using Excel to plot this, but I was concerned that the length of the video will be large, so I avoided that. But it is not very tough to visualize this. So first of all, w is a function, is a constant into xy, right? So here this will be negative, because b square is lesser than a square, because b is our minor axis, a is our major axis. So this will be negative into xy. So it means the warping will be constant for a constant x into y. For a constant value of x into y, it will be a constant. So these lines are lines of constant w, because the product of x into y is constant. So it also, whether it is positive or negative, or whether the warping is leading to displacement along positive z axis or negative z axis, depends on x and y. So remember, this is our positive x direction, this is our positive y direction. So here in this coordinate, x into y is positive, okay, but this constant term we said it is already negative, so this will be negative. Similarly, in this coordinate also, entire warping will be negative, other two coordinates it will be positive. So this lines denotes points where the warping or out of plane displacement will be constant. So as we know, one more thing we can easily reduce, as the product of x into y increases, the amount of warping also increases, okay, which means the outer lines where the product of x into y is more than inner lines will have more out of plane deformation or more deformation along the z direction. Okay, so I hope that it is clear. If you have any doubts, please let me know. So with this lecture we complete one more topic in this syllabus. So the next topic that we'll cover as per syllabus is how to deal with torsion problem in terms of strain energy. So till now we were dealing with the stresses, right? So in the next lecture we will cover the formulations related to dealing with torsion in terms of strain energy. Okay, if you have any doubts, please let me know. Thank you.